Hello, in this lesson we're going to learn about exponential and logarithmic models. These models are used throughout mathematics, science, business, economics, biology, and many other fields to describe real-world behavior and make predictions. We'll look at several common types of models, learn what their graphs look like, and see examples of how they're used to solve practical problems. Let's get started. In this lesson, we'll explore 5 common types of exponential and logarithmic models. We'll learn how exponential growth and exponential decay models can be used to describe changing populations and radioactive decay. We'll also look at Gaussian models, which are widely used in probability and statistics. Next, we'll discuss logistic growth models, which describe growth that eventually levels off. And finally, we'll examine logarithmic models and see how they are used in applications such as measuring sound intensity. By the end of this lesson, you should be able to recognize each type of model and understand the situations in which they are commonly used. There are 5 common mathematical models involving exponential and logarithmic functions. The first is the exponential growth model. This model describes quantities that increase at a rate proportional to their current size. Population growth is a common example. The second is exponential decay model. This model describes quantities that decrease over time, such as radioactive substances. The third is the Gaussian model. This model is often used to represent normally distributed data and produces the familiar bell-shaped curve. The fourth is a logistic growth model. Unlike exponential growth, logistic growth eventually slows and approaches a maximum value. And finally, we have logarithmic models. These models increase rapidly at first and then grow more slowly over time. In the next slide, we'll look at the basic shapes of each of these graphs. This slide shows the general shapes of the 5 models introduced in the previous slide. In the upper left, we see exponential growth. Notice how the graph starts slowly and then increases more and more rapidly. Next is exponential decay. This graph decreases quickly at first and then gradually approaches 0. The Gaussian model has a familiar bell shape. This type of graph appears frequently in statistics because many natural phenomena follow approximately normal distributions. The logistic growth model has an S-shaped curve. Growth begins slowly, speeds up, and then eventually levels off at a horizontal asymptote. Finally, we see the natural logarithmic and common logarithmic models. Both increase quickly at first and then continue growing more slowly as x becomes larger. Understanding these shapes is important because many real-world situations can often be identified simply by recognizing the graph. Let's look at our first application of exponential growth. Suppose a population of fruit flies is growing according to an exponential model. We're told that after 2 days there are 100 flies, and after 4 days there are 300 flies. Our goal is to find the exponential growth model and then use it to predict the population after 5 days. To do this, we start with a general exponential growth formula and substitute that 2 pieces of information provided in the problem. This gives us 2 equations involving the unknown constants a and b. We first solve the first equation for a. Then we substitute the result into the second equation so that we can determine the value of b. The algebra shown on the slide walks through this process step by step. Now that we've found the value of b, we substitute it back into our expression for a. After simplifying, we find that a is approximately 33.33. This allows us to write the complete exponential growth model. Once we have the model, making predictions becomes straightforward. To find the population after 5 days, we simply substitute t equals 5 into the model. The result tells us that the population will be approximately 520 flies after 5 days. This example illustrates one of the primary uses of exponential growth models, predicting future values based on observed data. Our second example involves carbon dating. Carbon dating is a scientific technique used to estimate the age of once living materials. Living organisms contain a small amount of radioactive carbon-14. After an organism dies, the carbon-14 begins to decay at a predictable rate. Scientists use this predictable decay pattern to estimate how long ago the organism died. The formula shown on this slide is in the carbon dating model. The variable r represents the ratio of carbon-14 to carbon-12 remaining in the sample after t years. Notice that the graph decreases over time. This reflects the fact that radioactive carbon is continually decaying. Let's use a carbon dating model to estimate the age of a fossil. We're given a specific carbon-14 to carbon-12 ratio and asked to determine the corresponding age. To do this, we substitute the given value into the carbon dating formula and solve for t. The algebraic steps are shown on the left side of the slide. By taking the natural logarithm of both sides and applying the inverse properties of logarithms and exponentials, we can isolate the variable t. Using a calculator, we find the age of the fossil is approximately 18,943 years. Rounding to the nearest thousand years gives an estimated age of about 19,000 years. The graph on the right provides a visual confirmation of this result, showing where the carbon dating curve intersects the given ratio. Next, let's discuss the Gaussian models. A Gaussian model is commonly used in probability and statistics to represent data that are normally distributed. The graph of a Gaussian model is called a bell-shaped curve. One of the most important examples is a standard distribution shown on the slide. Notice that the graph is symmetric about its center. For symmetric normal distributions, the highest point of the curve occurs at the mean. This means that the average value of the population can be identified by locating the x-value where the graph reaches its maximum height. Gaussian models are used extensively in statistics because many real-world measurements, such as test scores, heights, and measurement errors, tend to follow this general pattern. Not all populations continue growing exponentially forever. In many situations, growth slows down after resources become limited. A logistic growth model is designed to describe this type of behavior. Notice the S-shaped curve shown on the graph. At first, growth is relatively slow. Then the population experiences a period of rapid growth. Eventually, the growth rate begins to decrease and the graph levels off at a maximum value. This leveling off reflects the fact that real-world systems often have limits. Because of its shape, a logistic growth curve is sometimes called a sigmoidal curve. A common example is a bacterial population that initially grows under the ideal conditions, but eventually encounters limitations such as reduced nutrients or limited space. The final type of model we'll discuss is a logarithmic model. Logarithmic models grow quickly at first and then gradually slow down. Although this behavior resembles logistic growth, the shape of the graph is different because logarithmic functions do not level off at a fixed maximum value. One practical application involves measuring sound intensity. The decibel scale uses a logarithmic relationship between sound intensity and perceived loudness. The formula shown on the slide relates the intensity of a sound to its decibel level. Because human hearing responds logarithmically rather than linearly, logarithmic models provide a much more accurate way to describe sound. The graph shown here is simply an illustration of the general shape of a logarithmic function. This concludes our introduction to exponential and logarithmic models. Thank you for watching, and I'll see you in the next lesson.